My name is Yafan An. I'm the software architect for the Ethernet switching group in Juniper. Today I'm going to talk about a technology that we have in the Ethernet switching product lines called virtual chassis. So this is not a new product, but we do have new products that's kind of supporting this capability. We have one over there, that's the EX4550. So this is not a product announcement. We announced it.
Would you mind speaking up a little bit? It's kind of hard to hear you.
Okay. So
sorry.
That's okay. Thank you. So we announced that already, but that's kind of the products are supporting virtual chassis capability. Hopefully today, and I can give you a little bit more technical details that you can expect from some marketing and other type of presentations. So I have a few slides, and we're going to have two brief demos, one in the middle, and then I'm going to show you something at the end of the presentation. So this is an overview of the virtual chassis technology. So using some words, it's basically three things. Virtual chassis is a technology where a small to medium number of nodes can automatically form a system to appear as a single switch or router. Okay, it manages internal fabric based on shorted paths. That's one key thing we use in the virtual chassis technology, and we have multipath resiliency. Okay, so it appears as a single switch when you have. Yeah, so when this two forms a virtual chassis, it appears as a single switch or router, and then you can manage it using a single IP address, just like a single switch. And the switches can automatically join the switch. When you have a piece, a few boxes together, they can join the system together. And we support various type of resiliency features, link protection, multipathing, and of course dual homing. So this is the first set of switches. We delivered the virtual chassis technology. That is the EX4200. The idea there is to emulate a modular switch. So, you can take the line card and the control card and merge the control card into every line card, becomes a kind of a uniform.
Can you speak up, please?
So that's the recording. Yeah, the mic's not going to put it through the sound. The mic at the lectern is on if you want to use it.
Okay.
Just
Yeah.
yeah.
Okay.
Thank you.
Okay, sorry about that. So here looks better. Okay, so now the system will have the benefits of the modular chassis system. All the benefits, high availability because we have master and backup, routing engines, or the control plane, and it's easy to manage. It's an IP address, to manage, and you can, grow as you can add modules to it, so you can grow the size and the performance. So that's pretty much, I think EX4200 is very good for the access layer where you can have a lot of 1 gig interfaces connecting to desktops and servers. We also brought the virtual chassis technology to the access or some aggregation level layer applications with the 4500 and 4550. Those are 10 gig switches. So the 10 gig switch and the 1 gig switch can form a single virtual chassis, which is, appears as a single switch also. So when these two, type of switches form a single virtual chassis, they again appear as a single switch to be managed. And there's master and backup REs. RE is the routing engine, which is for redundancy. And you can add and remove members to the virtual chassis freely. With this two type of switches, we can support the 1 gig to 10 gig migration using a single system. You don't have to forklift your deployments. So we also have another line of products, EX8200. Those are chassis, 8216 and 8208. 8216 is the 16-line card, 1 gig or 10 gig line cards. We brought the virtual chassis technology also to this platform. In here, we did it a little bit differently. We used we completely separated the control plane and the forwarding plane in this platform for more resiliency and availability on the control plane. And then for this platform, we actually can support up to 8 members. That means 8 8216 switches can form a single virtual chassis, which effectively can be managed as a single switch. So those are the 3 product lines actually we support virtual chassis technology. So now let me talk a little bit more about what is the control plane features. The control plane basically, traditionally Junos is running on the RE card. Now, in virtual chassis, the RE manages all the network ports. But in virtual chassis, it manages all of the network ports from all of the, either it's EX42, 45, or 82, any switch in the virtual chassis, that's managed by the RE. And we have a second component in the virtual chassis. We ran a protocol called Virtual Chassis Control Protocol. VCCP manages all of the VCP ports. VCP ports are the inter-node links. And one of the design principles we had was to make RE, which is the routing engine, the routing protocols, the switching protocols, and the VCCP to be fairly independent. And we have maintained that goal pretty much to today, although we have gone through a few releases, quite a few products, quite a few platforms. The benefits of that is, with the Junos RE, able to manage all of the ports on all nodes, so we can inherit all of the Junos functionalities. And so we kept this modularity up to today. So the VCCP is used for fabric topology. One of the things we use, the topology is based on device topology or member topology, depending on the platform. For the EX42 and 45, we use device topology. So device topology gives you the benefits that you can find the shortest path between devices. Device is a PFP forwarding device, that you can use you can find the best path for forwarding. And the key algorithm we used in the discovering and managing the topology is shortest path, SPS. And actually, a VCCP protocol is designed based on ISIs. I'm going to show you a little bit, internally, when you look at the topologies of the virtual chassis, everything is ISIs based. And the encapsulation between the node is device aware or member aware, depending on the platform. So you can, so there's an extra layer of encapsulation. So with all of this, we can achieve better high availability and multipath resiliency features over there. So now I'm going to show you some of the internal stuff. I think I can do it over here. So now this is a a virtual chassis formed by with 48216s. These are the the four big switches. In the middle is an Atlas device. It's kind of it's simulating a 40-kilometer distance using a coil, right? So the two sides, these three things are 40 kilometers away from this. So because we have multiple type of ports that can support the VCCP protocol and the encapsulation, so they can, you can have a distributed core network that's sitting across 40 kilometers or whatever distance you have. And so this is the diagram. Actually, you can show that in your, now I have the access to the system. So what you can see is, for example, this is number 1, number 2, and 3. These 4 are the big switches, over there. And number 8 and 9 are the 2 extra REs to control the routing engines. So basically, if you can see, this is a neighbor list. Just as a neighbor list you see in ISIS, when you have a network of ISIS node, then this is what you see. So this is just to show that. And then you can actually show the active topology of the network. So you can see, from number 3, and these are the destinations, 8 and 9 are the control 2 REs, the control plane entities. So the path to other members of the virtual chassis, you can see it over here. So for example, from member 3 to member 0, you have 2 passes over here, which is through member 1 or through member 2. So this is what you can find out from this type of show commands on a virtual chassis, 8200 virtual chassis. The same thing for 4200 and 4500. It's always topology are managed by VCCP. So maybe a slightly more stuff. So protocol, like I said, is ISIS, right? So from here you can actually show, adjacency. It's all this. Here you can, see all the ISIS stuff. How many, partial LSPs, complete LSP sinks. All of that are shown over here. So from, at this moment, because we use ISIS and the separation of RE and VCCP, we can show you some demos how we do nonstop software upgrade and LSU in a virtual chassis. So that system should be here. So the previous picture is just part of this system, actually. So this is a 45 and 42 virtual chassis, and this is the one I showed you, the 48200 VC. So there's 2 VCs over here. We use AEs, so you can do home, you can do that. So what we're going to do over here is to show you the NNSU feature over here. So Salman is going to show you the demo at this moment. Is he on right now? Oh, you can come over here if you want.
Yeah, plug in.
This is
Is it? Oh, it is? Oh. Yeah, I knew it was on the back there. I'm like, what is that?
So right now I'm in the 4200 DC, which is a combination of 4200 and 4500. So right now I'm running the 12.1 image. So I will go and update it to 12.2.
So what he's going to show you is that we're going to start the NSSU process, and he has Spirent connected to all of the systems, and eventually you can, from the Spirent system, you can see, how much loss is there. So usually it should be pretty short. Should be
So
below
there are two systems, so I have to give the image name for the both. So one is the 4200 and one is the 4500. So after doing this, I'll go back to the Spirent. And I will run it for 1500 seconds.
Easier than the XU tester. That's right. Take a look at it and put the breaking point points.
So now the traffic is running, so it will run for 25 minutes. In the meantime, I'll go back and do the upgrade. So first it will do the backup switch, and once the backup is done, it will do the master. But there will be a minimal traffic loss.
Okay.
So are you basically going to fail over then? You're going to fail over from
Right.
your master?
They will do it. Yeah, once the
Yeah.
backup is done,
Right.
it will do the switch to master, and then master will upgrade itself.
Right.
The old master.
Yeah. So the procedure is kind of like, if you do it, you issue the command on the master, right? The master will do it. First, it will switch, change it to backup, and like the other one, take it. That should be lossless because all states are synced. And then it's cranking the software, putting into maybe some of the line cards, and then reboots itself. Before that, it's going to prep the ports. If you have lag, all of the signals are properly handled, and then let the traffic switch over. And then when it boots up, it comes back.
So when you're all done, you're back on the supervisor, you're back on the master that you were originally.
Yep.
Okay, so we can let the thing run. The reboot process is not that fast, so we can finish a few more things, and we can see the results. Yeah. Okay, so. Okay, this one is reacting a little slowly. Not bad. Okay, so now we kind of covered the control plane, some high-level features of the control plane of virtual chassis. Now I can get into a little bit more detail on the data plane, how we have done it. So I want to talk more about the 8200 VC because it's a little, so it's more. It's more difficult to get it to work on this platform. As you can see now here, I have a logical view of each 8200. Each 8200, it has a internal fabric. The PFE devices are connected kind of point to point through the fabric. And if you form a virtual chassis with another one, 8200. And then you can connect some ports between the devices, like I said, we form VCP trunks automatically, depending on how many, if you add a ports connection, we form trunks, trunks, or it's kind of like a lag. You can do load balancing between those links. And the packets traversing the VCP links, we use that encapsulation, the internode encapsulation we have. So for example, if you have a packet coming in from here and then going out on the same chassis, we actually just look up the device port on the local chassis goes out, which is simple. It's like the single chassis, right? If it goes out on another one, we actually put the trunk ID of the VCP trunk as the destination goes here. So at the destination member, we actually do a second lookup. Like I said, for certain virtual chassis technologies, we do one lookup. For transit, there's no second lookup. But for 8200, we actually do a second lookup on the second member, so you kind of reach to the right port. So this is just a repeat of what I said. If it goes to the single chassis, we do the port lookup. Going to another chassis, we actually slap the trunk ID, so it goes across the virtual chassis. So here, if you look at how we actually do, I probably don't have the right set, the entries in the demo system, so I just did this. So on the route engine, so you can see, VCP ports are actually not managed by the RE. So if you say, a MAC address is learned on this port, it's on this VLAN, that's what the RE knows. But in the PFE, there's two cases. If it's a local chassis, it just looks up the port device and port number. But even for non-local, so for the RE, it's still the same data. But in the two members, the first member, the ingressing member, it shows the trunk, the VCP trunk as the destination. And at the destination member, it shows the device and port. That's how we actually done the forwarding on the virtual chassis. And the multicast, there's a little bit more thing over here. One is because the 8200, the device does binary replication to the fabric and multiple replication to the network ports local to the device. So we arranged the PFE devices into a binary tree. That's how we do multicast replication. And each replication tree is inside the internal fabric of a 8200 is represented by a fabric multicast group, FMG. That's, if you have multiple replication trees, each one will have FMG in the fabric. And multiple FMGs, we can, one of the features we use, the multiple FMGs for load balancing is to, when you have AE devices that, for example, for this, you can 4-link AE device, and then you can have 40 gig of multicast traffic going through. Between virtual chassis members in the 8200, we formed a source tree for each source in the member, in the virtual chassis. So we do 4 source tree based multicast distribution among members. So there's, if you have a 4-member VC, then you have 4 trees that you have to calculate. So the loop avoidance in multicast is based on source ID filtering. So we actually reserve a number space for the member. So we reserved about 16, so we can eventually, using the same software, we can upgrade it to 16, I think. So 16 member VCs. then we're going to have, we use the, so the encapsulation when the traffic comes through one member, the encapsulation will include the source ID, the member ID in the encapsulation. Of course, there's a whole bunch of other things, so that's one of the ideas we used for loop avoidance. So here's some details. Actually, I can show you, but so another technique we used very extensively in the virtual chassis technology is trunk or lag. So remember we said, for for VCP trunk, we actually automatically forms trunk. And with that, the same, there's some other techniques we use for lagging. One is we call it local bias. If you look at this picture, so you can see, so if the two members are forming a VC, so obviously you can have another port that connecting to, so you can have the two links, lagged across a virtual chassis. So it's kind of like a multi-chassis lag, but for VC, that's by default. And we have another, if we have another Tor with the same kind of lag over here. So in this picture, if in the regular mode, so traffic coming through the link over here, this traffic may be split into this and this path to reach this lag. Similarly, from here to here and then here. So that's without local bias. So because traffic comes to here, we can find that the destination is already here. You will take the local lag, local link. Same for the traffic coming to this box. What we have done over here is a improvement over the regular trunking arrangement that we actually, once we have those ports, we can actually ship the traffic right away through this link. So that's what we call local bias.
So in the diagram here, in the previous diagram, it shows the fabric as being that circle inside of a chassis. And I guess my way of thinking was the fabric was the entire architecture. Is the fabric as described by Juniper something that lives inside the chassis, or is it the entire architecture?
No, so there's, the fabric is kind of a overloaded terminology here. So for each 8200, we have an internal fabric. We can call it internal fabric. That's, based on our internal chipsets, every device is connected to it. But between chassis, between members, we also call it fabric. It's kind of, external fabric, virtual chassis fabric. So we also call that a fabric. So, but for virtual chassis, the fabric means, the ones, the traffic, those VCP ports.
Okay.
Yeah. So it's two-level
So it's
traffic.
overloaded term.
Right, overloaded term. For the 42 and 4500, we actually, the fabric is purely between devices. 8200 is between members.
Okay.
Yeah.
Those are the more sophisticated
Right.
connections inside the
Right, so this is a two level. For 4200, that's a single level.
Okay.
Yeah. So that's the, the lag feature we just mentioned. I guess if you have no questions, we can come to, we have another demo. It's almost over, the other one.
We have another 10, 12 minutes.
Oh.
We don't have to fill up the 10 or 12 minutes.
Okay, yeah.
So just as a little bit of context in terms of where this presentation came from, I'm Abner.
Hey.
Nice to meet you. I've
Fine.
been away all week. Hey, everybody. So for a little bit of context, I don't know if those of you who remember the first network field day, where we went through the 8200 and there were a whole bunch of questions around how does it fail, right? And at the time, I think there was some confusion in terms of what was the questions you guys were asking about, how does it fail, were actually taken by the presenter at that time as, I think the Cisco thing's better, quite frankly. And as it turned out, and we figured out later, you guys didn't like the way that VSS works either. And so, we wanted to give you an architecture and a view into that. So given that context and given what you've heard just in the last few minutes, any other questions before we transfer over to take a little bit of a different tack into security?
No, I like this because I can't find any documentation on how this works on the website.
Okay.
And so it's been pretty valuable. It'd be nice if we had some more transparency overall and things like this, because I can go to other people's websites and get architectural white papers that explain how the traffic flows, so I feel I understand how the product works. So that presentation is...
Calvin, you heard that?
Otherwise, if you can just ship one of these to Ivan and let him play on the console,
Wow.
then you'll have your documentation.
There's actually a large container crossing the Atlantic.
But I mean, and that's not a criticism, I'm just saying,
No,
that's all we need. It doesn't need to be any deeper than this, so we feel like we know how it flows. We get confidence that we comprehend what the system does and how it does, and that it should not just be so like, if the vendor says it's true, that's because it's true. Because some of us need to operate at a more competent.
Right.
We'd like to have a greater understanding, and a white paper that just says this is the architecture.
So
Yeah.
let me ask you a question.
Yeah.
So we've had various forms of virtual chassis in the market for 3.5, 4 years now.
Right.
What have we learned along that time? Like, what did we get right at the beginning, and then what have we sort of fixed?
Well, so I think from my perspective, some of the design principles, I think that it's pretty powerful. It's pretty powerful. If you look at how we form, of course, from a product delivery point of view, we deliver that 4200 VC initially, right? So people may call it just stackable. So each box has 2 ports. You can only have a ring topology, but it serves the purpose. Covers a big market segment, I think. But the same design principle were applied to the 4200 VC. Carries over to 45, 4550, and then 82. I think we're continuously investing in
Are there
virtual.
differences in the implementation that have gotten better in different software releases over time?
Right.
And what
Yep.
is it that we learned? Did we learn, like, I don't know, fixing split brain stuff, or?
Well, I think what we learned is, this thing is pretty complex to make it work. Like you said, it's not a simple thing like, of course there's bugs, everywhere, but you have features that kind of, depend on certain, things, software that has a bug, and then you kind of, you got screwed. But I think the design principle was there, we have to, because of the complexity, we have to, probably work a few rounds on it.
So let me turn the question back to you guys and Craig to sort of riff off of what you were saying. When I think about what do you need to see, and what are the concerns that you run with, what is it that you're looking for when you're?
So you did the command there, showing the status of the ISIS.
Yeah.
I can't visualize what that means if I don't understand this, if I don't have this map of how the infrastructure goes together. So that show protocols, and seeing the IS database as far as it relates to the VCCP protocol has no meaning if you don't understand how the switch fabric architecture looks and
Right.
where they are XRE and what's the fault. Does that make sense? Because otherwise you're sort of staring at that going, I think it works like this, and then you don't know how your product works, and then you lose faith in how the...
Right, but I think, with this presentation or this talk, when I showed you that, show topology, how to link, it's basically when you do show virtual chassis active topology, it gives you, the next hops in that SPF tree you calculated to a destination. So
Yeah.
if you have one path, it's going to show you 1. If you have 2, it's actually show you 2.
Yeah.
So basically, based on that show command, you can build the topology I showed over here. And on top of that, you can see, how many, hellos or how many, LS, PSNP or CNSP you transmitted, all
Yeah.
of those things you can see. So basically, it's managing that. They also talk about the separation between the Junos RE and the VCCP
Yeah.
protocol. So that kind of design principle, which carried us, through to this day, that's still there, and make sure the topology inside a virtual chassis are completely managed by VCCP.
Yeah.
And we just, the VCCP just manages, the different VCP links, when do you form a trunk, how do you program the source filtering and all of that, and push it down to the packet forwarding devices and gives you a fabric. So this is kind of, I don't know the term, marketing terms, maybe network fabric or whatever, that's the thing. We can actually form all of that
Yeah.
through this protocol. Yeah.
So that makes
Great.
sense.
Any other questions?
I've got a general question more so before we segue into security,
Sure.
which someone in here may be able to answer. I've got a
Mhm.
massive Cisco background, and I'll
Yep.
be honest there, I'm more biased to Cisco than Juniper. I've been using it most of my career, so I've written it down here. It's fine in times, it's a huge pain to work with, and that's probably what most people would say too.
Which is a huge pain to work with?
SysIOS
Okay.
is I see people around the industry starting to, what they're starting to do with additional program extensibility with the operating system, so Junos or even iOS, others start Brocade. That's going to require additional visibility into the operating system itself. What is Juniper doing to create more openness with Juniper, and along the lines of what's being done with something like OpenStack?
Mhm.
Is there anything that's
So,
It's-
yes, and I
it's
think
bit
we're
of-
going to see some of that next.
not so much or even automation, but even just more transparency as well?
Sure, well, Derek, you want to take that one, or Mike, maybe? I don't know if Mike just stepped out. That's a great question for Mike.
Right,
Is
actually,
Calvin
so
here?
when we get up to the automation piece, we'll dive into that a little bit. So what do you mean by like transparency and visibility in the operating system? Can you clarify that?
If we're looking to move forward into the whole SDN solution, that whole, you've got, well, Tom and I was discussing this, and he had some good points about this, but I found that there's more information out there from other vendors than you guys. It seems that you've been a closed book in regards to some of this, but I haven't been able to find the same quality of information I have from Brocade's solution or other things with Juniper. That could be me being totally missing the mark of my searching, or you're waiting to do something.
Okay. So that's kind of like what Greg was saying, a few minutes ago, like,
Yeah.
so is that, I mean, do you all feel that way? Is it, would you like to see more transparency, more sort of insight into, for instance, how things work, or?
And I keep coming back to this, and it's actually something I put in my blog post. QFabric is, for lack of a better term, a giant black hole. Well, it's a little bit better because when the data goes in, it actually does come back out. But we don't know what happens inside of QFabric. It's magical. It's unicorns and fairy dust and things floating around until somebody actually looks at it and goes, oh, it works like I thought it worked. Why was there a need to hide that information? I mean, I understand that there's competitiveness between certain people in this area and they don't want to really share the secret sauce, but there's nothing magical about it.
Yeah. And I mean, the other thing is that I find it helps
Could
having
be.
a vision of how the architecture works. So if
Yeah.
I'm configuring and troubleshooting, it also means I can design around any weaknesses,
Right.
and then I don't run into potholes.
I'd rather know about those things up front than finding out about them when I'm cursing at somebody, especially if it's JTAG.
Yeah, no, that's very fair, and I think, in specifically with QFabric, what we've seen is, we wanted to have the conversation around the possibilities of what QFabric creates and what it enables, as opposed to spending all of our time talking about how it works.
Yeah.
Now, that said, there are people and customers like you guys who, in order to feel like it's a trusted entity, you want to pull off the covers and see what's really happening there. And that's important to understand the limitations of anything that you're building.
Yeah.
So I understand that, and actually had a very similar experience this past week.
I'll make sure open it up.
That's a different story from here. But I think
Let me
that's,
know
you
how-
know, that's good
how
feedback for
long
us,
is that.
Yeah.
for sure. And,
I mean, that presentation was pretty good. Just take that and put it in a white paper with some words.
okay.
Like
Yeah,
this.
and some of that might be in white papers that are just hard to find or
Well,
aren't
they're all in
grouped properly,
PDF
so,
format,
so we'll.
HTML
take that.
web pages.
Well,
Example.
I don't, yes. Some battles are easier to fight than others.
Yes, I understand. I haven't given up yet.
and so I mean, just to kind of follow up on what they're saying from my perspective, you know, the day of the Iron Curtain, you know, that kind of needs to come down.
Yep.
We're breaking down silos in compute and storage and networking. So they're really, you know, I think we need to kind of look at how vendors operate, and because if we're going to plug all this together, we really do need to understand, even dare I say, grow together.
Yep, yeah, I agree, for sure. Cool. Great, well, thank you very much.
One more thing.
Thank you.